In this video, we have a large storage tank. It is filled with water to the top here, and then it says there's a hole that is located 17 meters below the water level, and it says the rate of flow from the leak is found to be 2 times 10 to the negative third meters cubed per minute. Okay, and it wants us to do A, B, and C. All right, let's go and crack it up. If you need to, pause the video. Otherwise, keep up. Part A wants us to find the speed in meters per second at which the water leaves the hole. So again, here's the hole. It is located at a distance 17 meters below the water level. So to do this, the first thing you need to apply is Bernoulli's principle. However, I can cancel a bunch of things out for this particular problem. We know that P1, if we take the starting point to be at the water level surface here, the atmospheric pressure here is 1 atm. Likewise, at location 2, because the pressure at the top of the storage tank that's open here, and then the atmospheric pressure at location 2 is the same. I can cross out P1 and P2. And then likewise, I can go ahead and cross out 1/2 rho V1 square. Initially, the water was not moving, so V is just 0, so that term is going to disappear. And then the right side, I can go ahead and cancel the second term here, rho GH2. That's because if I choose the reference line here, where the water leaves the tank as my 0, because that's essentially as low as the water level can flow out, because after it gets to here, the remaining water stays in the water tank. Okay, so I'm going to call this H0, and if I call it H0, I can go ahead and cancel H2 out. Or if you want, you can just look at the change in height. How much has the water level, come down by? Okay, so if you want, you can just do H1 minus H2 if you measure from ground up. But I'm just going to call this H equal to 0 just because I want to stop where the water level is going to pretty much stop flowing. All right, on that, so on the left side, you have something that resembles PE, gravitational potential energy here, except this is now in terms of fluid dynamics. Rho GH1, the initial height, and then on the right side, it resembles kinetic energy, which is 1/2 rho mv square. When instead of m, this is rho for density. But you notice here on the left side and on the right side, we have density, and it's the same fluid. So we can just go ahead and cross density out. So to get v squared by itself, all you have to do is multiply both sides by 2. These are the only two remaining terms, and then therefore to get v by itself, after you multiply by 2, just take the square root of the whole entire term. Alright, so in that, here g is a constant, and then h is a height of 17. So the water level has dropped by a distance of 17 meters, so I'm just going to go ahead and plug that in. So in the diagram here, you notice the water level, whatever it was, it's going to go down to where the hole is, which is 17 meters below the water level surface. So this is pretty easy to do. I'm just going to go ahead and crack out the calculator work here, g being 9.8, and then the height here being 17. Here you're solving for speed, so you don't really need to put negative 9.8 and negative 17 because the square root of a number will give you a positive or a negative number, but the question asks for speed. So I'm just going to go ahead and just use the absolute value here. So if you do all this correctly on your calculator, you should get a speed of about 18.25 meters per second. That's the answer to A. Now, part B asks us to determine the diameter of the hole in millimeters. So in order to do this, you do have to recognize that, one, you are given the flow rate, which is 2 times 10 to the negative third meters cubed per minute. So let's go and crack it out. Here, the flow rate function that I'm going to go with is A times the speed. Okay. Why? Because I'm given the flow rate and I'm asked to find the diameter of the hole. I already know what V is, all right? So in order to find diameter, I need to find the radius of the hole. So I'm just going to use this function because I know Q, I know V. The only thing I'm missing is A, but once I know A, I can find radius. Once I know radius, I can find diameter, simply just multiplying that value by 2. Okay, so there's a reason why I'm going to go with flow rate equals A times V, the area times the speed at that particular cross section. All right, so flow rate here, I'm just going to plug it in because it's given to us as 2 times 10 negative third meters cubed per minute, and then the area function is just pi r square. Okay, and then V, again, we already found that from part A, which is 18.25 meters per second. So, but I notice here the flow rate is given in meters cubed per minute, right? On the right side, my speed is 18.25 meters per second. So right away, there's the discrepancy in the unit of time. Okay, so here I need to convert minutes to seconds. So every minute there are 60 seconds. So therefore, I'm just going to take this value and I'm just going to go ahead and multiply by 1 minute, but at the same time divided by 60 seconds. So if you do that correctly, you'll get a value of 3.33 times 10 to the negative fifth meters cubed per second. So it's important that you you convert minutes to seconds so that the units matches. So now that I have meter on the left side, I have meters on the right side, I have second on the left side, I always have seconds on the right side. As you can see, units will naturally cancel out. Okay. Other than that, so let's go ahead and solve for r square. To solve for r square, I want to go ahead and divide both sides by pi and 18.25. So if you do this correctly on your calculator, if you do 3.33 times 10 to the -5th divided by the product, the whole pi times 18.25, you'll get about 5.81 times 10 to the -7. And the unit here is meters cubed because this is, meters square. On the left side you have meters cubed, on the right side you have meters, so one of the meters will cancel out, leaving you with meters square. And if you take the square root of the whole left side and right side to get r, you'll get a value of 7.62 times 10 to the -4 meters. Okay, but the question didn't ask for radius, it asked for a diameter. So once you find r, you can just literally find the diameter by simply taking the value that we just calculated and multiply it by 2. The diameter is twice the radius. So here I just made a statement, d is equal to 2r. So there's the 2, r we just found, and that'll give us an answer of about 0.0015 meters. However, part B asks us to find it in millimeters, so all you need to do is convert to millimeters. I'm going to leave the conversion up to you, but if you convert it correctly, you just get a value of about 1.55 millimeters. Okay, and then let's go ahead and do part C. Part C wants us to find, what is it? How far from the base of the tank you would have to put a bucket initially. Okay, initially, because as it drips, the water keeps receding towards the base. But here it says initially, so let's go ahead and do that. It says what if the hole is 10 meters above the ground. So to find where you would need to place the bucket initially, I would just go ahead and set up my kinematics equation. Delta x is equal to Vx times time. We know Vx already, Vx being 18.25 meters per second initially. Okay, and then I don't know what time is, but it did say that what if, right, the hole is 10 meters above the ground, which means the water would fall down 10 meters. So I can use another kinematics equation, and I can just go ahead and solve for t. So here, delta y is just 1/2 gt squared. Delta y here is going to be -10, and then g here is going to be -9.8. If you use kinematics, if you want to get all technical, the displacement here is falling down, so the delta y is going to be -10. And then because if you're considering directions down is negative, then acceleration due to gravity will also be negative. So if you do that correctly, you'll get a value of about, I'm just going to skip all the algebra here. For t, you'll get about 1.43 seconds. Okay. Now once you know t though, you can just literally just plug it back into your delta x function earlier. So again, we already know v from part A, which is 18.25. I had a yellow t in yellow there because that's what we need. And then once we have t, that's 1.43, literally just multiply, and the bucket should be placed at about 26.1 meters from the base of the storage tank here. Okay. All right. I hope that helps. Stay nerdy. Don't be whack.